So, welcome to section 9.8. We're going to hit this section to just talk about some axioms, some key properties of probability, and how we can use those to our advantage. And then we're going to also talk about expected value, which is a very important measurement within probability. So, let's talk about some axioms. So, first off, some of the axioms exist not just in some situations that we have talked about, where we're talking about coins and other things that are all fair. But when we're talking about probability in general, what are some properties we can always come up with? Well, in 1933, Kamal, I can never say his name. This the Russian mathematician came up with this, where he showed that for any probability, it's always between 0 and 1. So obviously, everything is going to be between 0 or 1. So if I get a probability that's negative, that's bad. Probability that's bigger than 1, that's bad. The probability of nothing happening is 0. So 0 means there's no possible options. And if I ever get a probability of 1, it means that I'm actually accomplishing every possible solution is what I'm actually looking for. So both what I'm looking for and the possible outcomes are identical. Has to be the whole set. Now, the probability of two sets of outcomes, if they are disjoint, meaning they have nothing in common, then the probability of their union of A or B is probability of A plus probability of B. That's kind of a very valuable idea, and it kind of sets up some key things. So let's just kind of look at an example, and we're gonna go through this, some of the key aspects of this, and talk about why these are so important, these axioms. So let's just remember in a sample space, you have all the outcomes and that the event is a subset of the sample spaces. So let's look at an example here where A and B are events. So there's things within the sample space S. So if A and B are disjoint, could the probability of A be 0.6 and probability of B be 0.08? Now, initially, when we look at these things, we're like, these are both between 0 and 1. That's good. However, since they're disjoint, the sum of their probabilities should be the probability of A or B. That's probability of A or probability of B. That summation is 1.4, which is bigger than 1, which breaks that thing. So that means that axiom 3 or axiom 1 has to break. Axioms in reality are simply things that we assume to be true. They're actually not things that we can prove. They're basis upon which we build key properties. So they're assumed properties that are true, and that's just pretty much the general definition for probability. All right, so another aspect is, let's look at this. We want to show the probability of the complement is equal to 1 minus the probability of an event. So one of the things that we can do for this is simply that any set intersect its complements can be empty, because remember, complements, they don't share anything. Secondly, their union is everything. And so therefore their union, the probability of the union is probability of A plus probability of A complement, which is the probability of everything, which is 1. And then we simply subtract probability of A and we get right there. So because we have this equality, we're good, and it's pretty easy to work. So a couple key things to remember is this key probability of complements. This probability of a complement is equal to 1 minus probability of A. This is something that I hit on previously, kind of mentioned sometimes it's easier to count what I don't want rather than count what I want. And then secondly, down here, the probability of A union B is equal to probability of A plus probability of B minus the probability of their intersection. Now this, by the way, is a generalization for probability of De Morgan's law. And that's kind of a very valuable thing to use. All right, so let's talk about how we can apply this to a case. Suppose I want to find the probability of that a card is a face card, Jack, King, or Queen, and it's one of the red suits. It's hearts or diamonds. Now, there are 4 suits, so there is going to be 12 face cards in general. And each of these hearts and diamonds have 13 cards. So there's 26 here. However, so we can do the probability of it being a face card is 12 out of 52. Probability of having it be a red card is 26 out of 52. But there is overlap. What is the probability that's both a face card and red? Well, if it's face card and red, you're going to have 6. That's because you have 3 face cards in hearts and 3 in diamonds. So it's 6 out of 52 is that probability. So we literally line it up there. 12 plus 26 50, or 52 minus 6 over 52, which is 32 or 52, or approximately 61.5%. So the probability of drawing a card that's either a face card or a red card is about 61%. And that is kind of how we can utilize all these kind of objects to our benefit, is by sometimes we can't find something directly. So what if I knew this union probability, but didn't know the intersection? Well, guess what? There's ways to still find that again if we know the rest of the parts. All right, so let's talk about our last concept, which is called expected value. Expected value is actually essentially the average value of what I'm going to get out of something. So if we run an experiment a whole bunch of times, what value is really the most likely, the average value of everything? Doesn't mean it actually is, because when we do samples, it's totally different. But I'm saying, what is it supposed to be? Well, it's the sum of the probability of each event times the value of that event. So best to show this by using an example. So let's talk about the lottery for a second. Suppose you go buy a lottery ticket, it costs you $5, and 500,000 people are playing it. And there's a guarantee that one person is going to win the grand prize of $1 million. 10 people are going to get 1,000. 1,000 people are going to get 500. 10,000 people are going to get $10 a piece. Now that sounds great when you start hearing those numbers. You're like, sweet, there's a really good chance that I can do this. So I'm just going to write down a couple key things that kind of hit on this, and I want to point out why this is super valuable. So what's the probability of the grand prize? Well, the probability of grand prize is 1 out of 500,000. And the probability of second place is actually going to be 10 out of 500,000. Keep going on this whole thing. And so what we can do here is we can say the expected value, and then I'll show your book's strategy, which is slightly different, but this is the way that I always looked at it. Each person has to pay $5. So let's take each person. There's a guarantee that there's a 100% probability, or one, that they are going to pay $5 guaranteed. Plus, there's a 1 in 500,000 possibility that they're going to win the grand prize of 1 million. There's also the probability that they're going to win the second place, which is 10 out of that 500,000. It's 1,000. Plus, then you'd have 1,000 over 500,000 times 500 plus 10,000, not 100,000, just 10,000. 1,000 times 10. Well, if you do the calculations, this is going to be -5 for the first one. The second one is 1 million divided by 500,000. So that's going to be a +2. This one is going to be 10,000 over 5,000, which is 1 over 50. So this right here is going to be 1 out of 50. You can also figure out, if I cancel out zeros, I have 4 zeros, so cancel out 4 zeros down there. Well, 1 out of 50 is 0.02. Plus, this is going to be 500,000 over 500,000, so that's a 1. Plus, this value right here is 100,000 over 500,000, which is 1 over 5, or 0.2. If I add this up, and real quickly, you can see that this portion right here is going to be 3.22. Well, -5 plus that's going to be -1.75. $1.78. And real quickly, let's just talk about what that really means. That means if I buy a ticket that the average person is going to lose $1.78. So even the people who you kind of look at it and you're like, oh, well, I have a 10,000 possibilities of winning $5 essentially, because I'm going to win $5 in total for net gain. Essentially, this is figuring out what's our net gain overall. And that is where people get messed up with their heads sometimes in these things because they don't think of the cost as actually part of the calculation. They would only look at this part and they say, oh, the average person wins $3.22, and forget that that every single thing has to put in $5. So actually the net gain. Companies use this, especially insurance companies, to say, okay, this is how much everyone's putting in. What's the probability that we're going to lose this much? Probably this much. Because they want to end up, they have to figure out instead for them, it's all right, your average person's putting money in, except that's going to be a positive value that everyone's making a payment. What's the probability we pay out to them? And so we use this to our advantage. Now, the other way your book does it, to show you, is instead what it does is that it rocked up K is 1 through 500,000 and named each person essentially and gave them a number. The first person got a net value of this, which is the 1 million minus $5. The next 10 people, that's from 2 to 11, got 995. That's 1,000 minus 5. Then starting the next one, which is 12, for the next 1,000 is 495, and so forth. And this gets to where some of this numbering throws people off, and that's the part that is kind of bad, because then you get this summation here. We have 1 over 500,000, but now we have to figure all of these numbers, which it turns out are 999,995, and then 10, because remember we are winning $10 times this. So that's how much those people were winning. And you throw all these numbers in, and again, guess what? You get the exact same value. I prefer my strategy because it's the way that I always learned. This one that your book does, it's different. I'll let you look at it and play with it. Let me know what questions you have. Good luck.